Planning a trip with friends sounds fun, until you realize you're actually running a multi-agent negotiation with hard constraints. If you've been following LLM agent research, you've probably seen benchmarks for travel planning. But they all share a critical blind spot. They assume a single user. In the real world, travel planning is a group activity. Preferences are hidden, budgets clash, and someone always wants to skip the museum for the beach. To actually evaluate whether AI agents can handle this, researchers recently introduced GroupTravelBench. Today, we're breaking down exactly how it works, why multi-user planning breaks most current models, and what the benchmark reveals about the future of agentic coordination. Existing benchmarks treat travel planning as a deterministic optimization problem or a single-turn dialogue. But real group planning requires three distinct capabilities that most agents haven't been rigorously tested on. First, elicitation. The agent must proactively drive multi-turn conversations to uncover private, incomplete preferences. Second, coordination. It needs to detect conflicts, propose compromises, and sometimes split the group into sub-itineraries when preferences fundamentally diverge. And third, planning. Generating a feasible multi-day itinerary that balances overall group utility with fairness. GroupTravelBench is the first benchmark designed to evaluate all three simultaneously, in a single shared environment. Let's look under the hood at how they built it. The benchmark doesn't just generate random prompts. It uses a four-stage synthesis pipeline grounded in real-world data. They start with 22 social archetypes, thousands of anonymized user profiles, and over 300,000 points of interest from map services. But the real technical innovation is in how they model preferences. Instead of a single static vector, each user maintains three coexisting preference tables. You have the original ground truth table, which stays hidden from the agent. You have the agent's inferred table, which updates as the conversation progresses. And you have the effective preference table, which applies any accepted compromises in real time. This tripartite structure is crucial, because it lets researchers measure exactly how well the agent tracks user preferences versus how well it actually executes the final plan. The interaction happens in a synchronous group chat environment. The agent doesn't just dump a JSON itinerary. It has to navigate a shared conversation history under a strict scheduler. The system forces the agent to mention specific users when asking targeted questions, while preventing it from broadcasting statements to everyone at once. The user simulators are behaviorally constrained. They won't volunteer information unless asked, and they only speak when directly addressed or when a hard preference is violated. When conflicts arise, the agent can request a compromise. If a user agrees, the simulator emits a natural language response alongside a machine-readable JSON marker that updates the effective preference table. This makes compromise an auditable, deterministic event rather than a subjective judgment call. And the agent doesn't guess. It has access to a sandbox of 10 production-grade travel tools. We're talking POI search, route planning, flight and train search, weather lookups, and web search. To guarantee reproducible offline evaluation, every tool call is routed through a content-addressable cache containing over 300,000 real API responses. If the agent makes a slightly different query that isn't cached, the system falls back to an embedding retrieval and in-context learning simulator. It uses a FAISS index to find the top 8 semantically similar cached entries, formats them as few-shot examples, and has a dedicated tool simulator LLM generate a plausible, format-consistent response. This eliminates environmental noise while preserving realistic tool behavior. How do you score something this complex? The researchers use a dual-view evaluation framework. On the outcome side, they use 4 rule-based metrics. Preference coverage measures how accurately the agent collected hidden preferences by comparing its inferred table against the effective table. Group utility scores the final itinerary against those preferences, using a weighted system where hard constraints like budgets and must-visit sites carry a plus or minus 2 weight, while softer preferences like category likes carry a plus or minus 1. Group fairness measures the ratio of the lowest individual utility to the highest, ensuring the plan doesn't just satisfy the vocal majority. And plan validity runs 9 deterministic structural checks for things like temporal consistency, opening hours, and spatial continuity. But outcomes don't tell the whole story. That's where the LLM judge comes in. It evaluates process quality across 5 dimensions: factuality, tool use reasoning, interaction quality, conflict coordination, and plan humanization. To reduce judging noise, they implement a meta-evaluation step where a second model reviews the first judge's reasoning and applies a calibration score. The final process score is a weighted average that heavily penalizes hallucinated facts, redundant tool calls, or poor pacing. So what happens when you run frontier models through this gauntlet? The results expose some fundamental bottlenecks in current agent architectures. DeepSeek V4 Pro dominates in preference coverage and overall utility, largely because it aggressively drives multi-turn elicitation and uses significantly more tool calls per task. But here's the catch. Group fairness caps out around 55% across all models. When you scale the group size from 2 to 6 people, fairness degrades sharply. The data shows that coordination difficulty scales superlinearly with the number of stakeholders. Models can easily accumulate aggregate utility by satisfying the loudest preferences, but they consistently fail to distribute it equitably. Plan validity is even more alarming. Across every model tested, fewer than 11% of generated itineraries pass all structural checks. When you break down the failure modes, missing intracity transportation jumps out as the dominant error. Agents routinely schedule a sequence of attractions without explicitly booking the transit between them. Spatial continuity tracking is fundamentally harder than temporal reasoning for current architectures. And despite the benchmark explicitly rewarding compromise, the mechanism is severely underutilized. Nearly 70% of tasks receive 0 successful compromises. Most models skip negotiation entirely and fall back to a single-pass planning attempt, accepting lower fairness scores as the cost. GroupTravelBench isn't just a new dataset, it's a stress test for the next generation of AI agents. It proves that multi-user coordination, preference elicitation, and spatial reasoning are qualitatively different challenges from single-user optimization. The gap between what frontier models can do in isolation and what they can do in a constrained, multi-stakeholder environment is wide. But that's exactly where the research needs to go. If you're working on agentic reinforcement learning, multi-agent negotiation, or constraint-aware planning, this benchmark gives you a rigorous, reproducible surface to measure progress. I'll leave a link to the full paper and the code base in the description. If you want to dive into the prompt structures, the cache system architecture, or run your own models through the sandbox, it's all open. Let me know in the comments how you think agents should handle group conflict, and I'll see you in the next one.